Hello everyone, welcome to this video. Let's talk about fully connected feed-forward neural networks. So here is a diagram of a perceptron from earlier on in the course. And even though there's a lot going on in this diagram, hopefully you should understand what is going on. But let's make things a bit more condensed. Let's condense it to this. Feel free to pause the video. And then let's further condense it to this. So here's what it previously looked like, and here's what the more condensed version of the perceptron looks like now. And for the new diagram of a perceptron, the behavior remains the same, meaning we still have inputs, weights, sum, bias, activation function, and output. And you might be asking yourself why. The answer is future diagrams will have many perceptrons, so we need to be condensed. If we have many perceptrons, this will be quite crowded. So, perceptrons to neural networks. We can connect many perceptrons to form a neural network. Don't worry about these terms you see down here. I will explain them later in the video. So, a feed-forward neural network. Perceptrons are organized into layers. Perceptrons receive inputs from the outputs of the previous layer. Let's look at these two perceptrons here. They get their inputs from the outputs of the previous layer. And perceptrons pass their outputs as inputs to the next layer. So for these two perceptrons again, their outputs go to the next layer. Information only flows forward. In this diagram, this can be seen as left to right. So this is a feed-forward neural network. Fully connected layer. Perceptrons are connected with a weight to all perceptrons in the next layer. Looking at these two perceptrons again, the next layer also has two perceptrons, and these two perceptrons here are connected to all the perceptrons in the next layer. The perceptrons are in fully connected layers. PyTorch calls it a linear layer. So if we go to this file in the course directory, where we ran this file /model in earlier on in the course in our running a model video, if we scroll down, nn.linear and nn.linear, so yes, PyTorch calls it a linear layer. So for input, output, and hidden layers, the first layer is the input layer. It receives the inputs. For example, maybe x1 could be the age, x2 could be the height, and x3 could be the breed for maybe a dog or a cat, etc. These are just examples. Feel free to use your imagination. The last layer is the output layer. It produces the outputs. And in between are the hidden layers. So this is the model in the fcffnn.ipynb file. So this is what, right here, this is what the model looks like. Now you know that FCFFNN means fully connected feed-forward neural network. So, as a recap, connecting perceptrons, which does math with inputs, weights, bias, and activation function using layers, and then improving those perceptron weights through training, gives a model that can recognize handwritten digits with a 97% accuracy, which we saw down here. The input layer of size 784, since the images have a total of 784 pixels. You can do 28 times 28, get 784. In fact, if we look, here we go. So here's the flatten, right? There's the flatten. Input layer 784 pixels. In features equals 784. Now, how many hidden layers and perceptrons to use? So for this model, we use one hidden layer of size 256 perceptrons right here. Out features equals 256. And so you may be wondering, why didn't I use 10 hidden layers, 100 hidden layers? Why not use 1,000 perceptrons instead of 256? What made me choose one hidden layer with 256 perceptrons? One answer is you can experiment and see what number of hidden layers and what number of perceptrons to use in those layers works best. Although you might also want to think about seeing what others have done for similar problems or even recommend. And when it comes to the number of hidden layers perceptrons to use, you might think that more is always better, but there's actually a Goldilocks zone to it. Let me explain. If you have too few hidden layers and perceptrons, you get what is called underfitting. I find this very easy and intuitive to understand. Think of this as not studying enough for your final exam. But what if you have too many hidden layers, too many perceptrons? You would think that that's a good thing. But if you have too many, you get what's called overfitting. This is like overstudying for your final exam. You overstudy so hard that you don't actually learn the material and understand the material. You just memorize the answers to the study guide problems and the study guide questions. You just brute force memorize the answers. So when the final exam comes, since you don't actually understand the material and you just brute force memorize things, you fail the final exam. And you risk this happening if you have too many hidden layers and too many perceptrons. And of course, if you have too many, you get longer training, which means it costs more money. So again, this really is like a Goldilocks zone. You don't want too few, otherwise you don't understand it. And if you have too many, you also risk just brute force memorizing the answer, or your model does, and it's going to cost you more money. Okay, the output layer. Well, we want to classify images based on digits 0 through 9. So the output layer has 10 perceptrons. As we can see here, out features equals 10. If we want to classify images based on whether it is a dog, deer, or a donkey, then the output layer has 3 perceptrons, one for each of these things, dog, deer, or donkey. Whereas for regression, where the output is a singular number, maybe our model tries to predict the house price. If you give it the number of bedrooms and bathrooms, windows, and the zip code, or maybe we're a business and we want our model to give us the number of tennis rackets to produce to maximize our profits, etc. So for regression, the output layer has 1 perceptron, not 10 as we see here. If we look at this diagram again, it looks like, look at the outputs. Our model thinks this image is most likely an 8 because it has the highest output, with second place being a digit of 3, which actually makes sense, because you can imagine that if someone has really bad handwriting, their 3 could look like an 8. Now, I'm going to reuse a slide from earlier on in the course, but make an addition to it. Weights are parameters. OpenAI's GPT-3 has 175 billion parameters. Biases are parameters too. meaning they are also updated to minimize the error/loss. So for this diagram I've shown earlier in the course, if we want to be more precise, this should be model, weights plus biases, and this should be update weights plus biases. Or if you want to be even more precise, we can use the term parameters. So this should be model parameters, and this should be update parameters. All right, let's do a pop quiz. Parameters, which are weights and biases. For this diagram of a perceptron, how many weights and biases are there? Or how many parameters? There's 4 parameters. We have 3 weights. You can think of each of these arrows here as a weight. 1, 2, 3 for 3 weights. 1 bias. We have 1 perceptron, and each perceptron has 1 bias. 4 parameters. This wasn't too difficult, hopefully. What about this network? How many parameters? Feel free to pause the video and take your best guess, or do the math yourself. The answer is 20 parameters because we have 14 weights. If you want, you can just count these arrows, which should be 14. Let me actually do that. 1, 2, 3, 4. Actually, no, never mind. Let's just do the math, actually. So 3 times 2 is 6. 6 plus 4 is 10. 10 plus 4 is 14, so we get 14 weights. And we have 6 biases because we have 6 perceptrons. So we get 20 parameters. And for the final pop quiz, you will definitely have to do math to figure it out, is how many parameters are in our model here. Again, feel free to pause the video and see if you can figure this out on your own. The answer here is, well, we have 203,264 weights because we do 784 times 256 plus 256 times 10. We have 266 biases because we have 266 perceptrons. And each perceptron has 1 bias. Add these 2 up, and we get a total of 203,530 parameters, which seems like a lot. I suppose it can be. But again, for comparison, OpenAI's GPT-3 has 175 billion parameters. And in the next video, let's implement a layer with 3 inputs and 2 perceptrons, which I have highlighted in red in this diagram. So yeah, thanks for watching this video, and see you all in the next video.